Hey everyone, welcome to TGIF. This week has been pretty big in Covenant. A couple of things. First of all, we do some housekeeping. We will talk about what the rest of the orders have been up to. With Covenants, we kicked off the Crusades. It's really interesting how these things happen and transpire because you spend a lot of time trying to figure out how can we build this system to push miners forward. So let's take a step back. So where are we with Templar? On Templar, we've trained the largest model ever trained over the internet, and it's gone quite well. So we're in the process of starting our next run with the architecture for our next run with SparseLoCo, which is our new optimizer that allows us to combine data parallel and model parallel training. So that's pretty interesting. But in the meantime, one of the things we noticed from Templar is the last run, it became clear at some point that miners weren't really able to optimize because when you combine the token price and the cost of B200, it came to a state where we couldn't really push the miners to outperform. So they didn't do badly, but compared to what we saw from our smaller runs, we said, okay, maybe Gauntlet, which is our incentive mechanism for Templar in its current form, maybe we need to adapt because one thing I love about working in decentralized training, especially within this scarce mindset, is that scarcity always breeds innovation. So what we're doing now is in the meantime, we're exposing different part of the protocols as competitions. And eventually, we plan to grow it into a way where we can direct miners towards neural architecture search or new algorithms that will power Templar. That's going pretty well, but unfortunately, the miners broke it in like a day. So Crusades has launched again today, and hopefully Hawkeye, who is managing them on Discord now, will be up making sure that miners are happy. Cool. With Basilica is also going well. There's two things with Basilica that we're pushing up. First, everyone's seeing what's happening. SAS is dead. But I don't believe SAS is dead per se, but the nature of distribution of how you interact with infrastructure, how businesses are formed, is changing rapidly. So we anticipated this in Basilica, and we hope to fully attach to the new agent narratives, which is agent-driven infrastructure. So we dropped a mock tutorial yesterday. I think people are already trying deploying more on Basilica, but that's to a taste of what we have. Hopefully, we'll get the new IM out next week because it really helps us scale dynamically to market demand and not pay too much. So we push miners to give us cheap compute and give us the compute competitively. So more from Basilica next week. Now, the last bit is Grail. So Erfan has been working on Grail for hold on. Erfan, how many months have you been on us now?
4 or 5 months, I guess.
Jesus Christ, it feels like 3 years with the amount of work you've done.
Yeah, thank you.
So what do we set out to do in Covenant Labs? It is to democratize intelligence. We want intelligence to be the commodity, something that's freely accessible from anywhere. Not only do we think this is a noble goal, we also believe that it can be immensely profitable when we create this vertical. That's okay. Because, when we started, I would keep saying, when I started Templar, it was a joke. It didn't look like it would ever be possible. And now they're like, okay, it's interesting. So the trajectory, we're definitely on the right trajectory, but we had a problem in that all we were doing was pre-training. And again, very naively, I didn't think that there was anything more because I just thought post-training is just like SFT. We just do a couple of tricks, but that is changing a lot now. And RL and post-training and all those bag of tricks starting to dominate a large part of the training process. Imagine being able to do pre-training as a service. Grail provides the other missing piece towards the whole pipeline, which is how do we decentralize the RL process, the post-training process. Now, RL is a bit of a funny mistress. With pre-training, it's not that messy. I mean, it's still messy, but RL is a different kind of complexity. Because with pre-training, you're just doing one thing one place within one core. At least in central training, you get your data, run over it a couple of times, run the backstep, update the weights, then you move on. But in RL, there's a two-step process. You have to run inference use that inference to update the model, update the weights, then update the inference workers again. So there's that kind of dynamics. The approach to decentralizing post-training for us wasn't straightforward. It wasn't like, again, we can say Templar was straightforward because we've done it for pre-training, but in hindsight, it wasn't straightforward. With post-training, right now, the thing we're working on is also expensive. It's the inference. So miners generate rollouts. Then with this rollouts, we update a trainer. Then we send the weights back to the miner. Now, this process is terribly expensive. So I'm going to let Erfan come on stage and talk to us in very simple terms, because this is not an academic conference and people listening to this need to be able to understand how important and how big of a thing you've uncovered.
Yeah, thanks for the intro, Sam. As Sam was saying, in RL, it's kind of different from pre-training. Pre-training, what you do is that you have a bunch of data and do next token prediction. You have a lot of data already, just consider you have a bunch of text and you're just training on those, right? It's just you have a trainer and you train on those. But when you do RL, it's kind of you have two different functions. One is inference and trainer. Inference generates the rollouts. Rollouts are like, when you talk to ChatGPT, you ask a question, it answers something to you. Those answers are the rollouts being generated. Those are inferences being generated. And it needs to generate these rollouts and give it to the trainer. And trainer improve its models by these new rollouts. And then it updates its weights. And then it needs to send these weights to the inference. So inference generates new rollouts or new inferences based on this updated model. So this part that kind of makes RL a little bit more tricky to optimize, because you have to both optimize a trainer and an inference engine or the inference node or something like that. So what happens here is that, at least in the thing we designed so far, we give the responsibility of doing the inference to the miners, right? Miners are generating the inference for us and they're generating a lot of rollouts for us. And we take care of the trainer. And as Sam mentioned, the main reason for that is that inference is super expensive. Inference is like 80% or more of the cost of doing reinforcement learning. So giving the inference responsibility to the miners financially and economically makes more sense here. So we do that, and that's the architecture we're dealing with. Harder and more challenging to do it in a centralized manner, just doing it in the data center. And some of those challenges that we had to deal with in a decentralized setting that we are also dealing with, one of them was verification, right? We need to verify that the rollouts that you're generating are coming from the same model that we expect you to generate it from, right? For example, we gave you this model and we want you to generate the rollouts from this model, but you can cheat the system and you can use another model to do that because it costs you less, right? So we needed to solve that problem. That problem has been solved to a good extent in the past few months, and we're still going to add upgrades to it, but it's pretty solved right now. But there are a couple of other issues as well. The most important and challenging one is the problem of latency. Latency means that when you get the rollouts from the miners, the trainer needs to send them the new weights of the model, right? It needs to send a new model that it upgraded, improved, or something like that. And this new model needs to be sent over public internet. Public internet is super slow compared to data centers. In data centers, you can send the model in a few seconds because it's so fast to just send it because they're so close by. They use really special connections and everything. So it makes it so easy to do that. But over the public internet, it's minutes. There was a paper by Promi Intellect that they post-trained the model, and it took 14 minutes to send the new weights to the people who are taking care of the inference. That's a bottleneck. That's what happens if you spend 40 minutes sending the rollouts. Your whole training paradigm is going to be 10 to 20 times slower than training in a centralized way. And that bottleneck can screw up a lot of things. So what we solve with Pulse here is we focus on this problem. We try to solve this problem of latency so we can send the weights to the miner in seconds instead of minutes. This is a really interesting story because I personally thought it's going to take us a lot of time to solve this issue because it's not an easy issue. Your model is really big and has so many parameters. It's gigabytes of data and you have to send it over the internet. And you have all these latency issues. Well, I was reading a couple of papers 2 months ago, 3 months ago, and I realized this common theme started showing up in different papers. There is a high sparsity in the model's weight. What that means is that when you train a model, only small set of the weights or parts of the model are getting updated. For example, only 1% of the model getting updated, right? After each of the trainer updates. It's not like 100% of the model is getting updated. This was really interesting to me because some of the papers said like 30% of the weights of the model getting updated. Some paper 20%, some paper 10. It depends on the model and lots of other hyperparameters and stuff. So I was like, okay, this is pretty interesting. I was wondering whether anybody has used this to actually improve this latency issue that I talked to you about. Because if like 1% of the model weights are getting updated, why we are sending the whole model? And this seemed like such an intuitive and simple idea to try. But the question is, all of the papers I looked at compare the model before training and 10 hours after training has finished, or 2 days after training has finished. They look at these two different versions and they're like, okay, there is like 20% sparsity, not 20%, like only 20% of the weights got updated, or 30% of the weights got updated. That's a cool thing to know, but I want to see how it's getting updated at each step of training. And each step of training takes a minute or 2 minutes. So I was wondering how it happens in that granularity, because that's what we care about when we are actually training a model. And if it is really low, then we can exploit it. But if it is only 30% of the weights getting updated, we can't get that much performance boost, because 30%, there are a lot of overhead of sending only a small portion of the weights over the public internet. That wouldn't necessarily be a good trade-off to do that. So I really dig deep and like ran a lot of experiments across different models. If you're familiar with the models released by Google, like Gemma models, or models that were released by Meta, which were like LLaMA models, and Qwen models like from, Qwen team, which a lot of people like those models and they're widely used right now. And I saw that same patterns just keep happening, right? And it's like the number of the part of the model that is getting updated after each update step is only like 1% of the model. So it's not like 30%, it's like 1% after each update. So I ran these experiments, I showed it in the paper like scientifically that this is true. I ran it to make sure that I get results that I can be confident on. I ran multiple times. I averaged through a lot of stuff, like a lot of scientific stuff goes through. This was shown in the paper. And I also investigated what is the cause for this and a lot of other stuff in the paper that you can look at. If you have also question about it, I can answer. But then I really exploited this and I looked at this like 2% of the model parameters that were being updated. I realized you can add another layer of comparison algorithms on top of this to even go beyond this than 1% of the model weight that you need to send. You can add another layer of compression and improve the performance even by 2 times or something like that. And I ran a lot of benchmarks on that as well. In the end, what happens is that we got over 100 times less latency or 100 times more SP in the case of sending the model weights through the network. 100 times is a lot. It's not a small number. It's crazy even to me. So what happened?
Let's go back one step and realize what this means. Now, again, it's always been decentralized trading is too slow. It will never work. But right now, we have instantiated the fastest decentralized trading instance in the world with a fraction of the resources. I think that gives a testament to both Erfan, especially because, dude, like Grail is one subnet I've never had to touch. I think I vibe coded a V1 and Erfan threw everything away. And the people at Basilica still get my AI slop from time to time. But it also proves that we can channel incentives to fund innovation, which I think is the very big Tensor thesis, is, being resource constrained in resource constrained environments. What would you do? You don't have the option to say, oh, we use bigger computers. You co-locate them. You dig deep into literature. You do research, and you come up with stuff like SparseLoCo, which is what we did for Templar, and now with Pulse, which we have done for Grail, and we can converge at centralized speed. Do you know how well, in terms of compression, this measures with pre-training? Can you compare it? Like, I know it's not like for like, but because our trainer is also a sync, you might actually be faster than Templar now. What do you think?
How it compares with pre-training? That's a good question.
It's a bit of a stretch, and we don't have any of the Templar guys.
Yeah.
Can you do like a rough approximation as Pulse versus SparseLoCo? You can't. I don't think you can you?
Yeah, I can look it up, but I'm not sure exactly. One thing I would say though is that what a SparseLoCo does is amazing. The thing that they did is crazy, especially communicating the weights. But there's two different distinctions. Like what they did was lossy and what we did was lossless. And what that means is that in our case, the weights are not going to be different. We're going to send them the exact weights they're not need to use, right, for sending the inference back to us. But what they did is that some of the weights get lost because of approximations. So what we do is there's no approximation there. Like it's 100% the same weights, the same everything, and the network and training is gonna work the same.
Sounds like innovation to me. So what are your next steps? Where are you taking Grail? Are we training? Because again, for me, I'd like to see a really good model come out of Grail. Something that can stand on its own 2 feet. So what roadmap have we got for us?
So I think what we want to show right now is that we almost got decentralized training and centralized speed now, right, by this improvement. So given that, we want to post-train a model that is actually useful to the community and also beat some of the benchmarks like everybody does, right? And the model that we are going to most likely train right now, I'm also getting the data, I'm building the data recipe and everything for it, is a model for generating or creating optimized GPU kernels, right?
That sounds interesting because there's a lot of people doing that. And if we can smash that, that really puts this technology at the forefront, which is interesting immensely.
I agree.
Cool. Thanks. And also something you'll be doing, Eugene and I were talking about this. We need to mine Erfan. So we need to figure out how to put a Grail model on top of Erfan and all of Tolcon's Erfan tokens and dump them. Pretty interesting. I think you might spend some time scoping that out. The problem is if we're trading our model, they can always snipe it and just put it on theirs. So we need to find a solution around that. But yeah, pretty interesting time. Good stuff. Thank you all for this week of TGIF. It's been a hard week currency-wise, but a lot of people on the team have taken sacrifices to ensure that we're anti-fragile because crypto is volatile. We run very lean, and I'm very grateful to my team for the dedication and staying lean so that we don't compromise my values. We will speak to you same time next week. Bye.
Bye, guys.